Your terminal is scrolling out of control, endlessly printing numbers until your program crashes. These crashes usually happen for two reasons. You built an infinite loop that never stops, or a logic skip bypassed your data entirely. The fix comes down to a single mechanism, the control variable. It acts as the steering wheel, deciding if the loop runs again or halts. Let's set a simple goal. We want to write a program that cleanly prints the numbers 1 through 5 and then stops. To pull this off consistently, we have to stop guessing. We need to treat loops as predictable machines that do exactly what we explicitly tell them to do. That brings us to the ICU Framework, a required operating manual for diagnosing and building structurally sound loops. This code snippet shows initialization, setting the control variable's starting value. Next, the control step, a Boolean expression boundary that must eventually become false. Finally, the update step modifies the control variable inside the loop. Missing that update is the direct cause of infinite crashes. Without it, the condition is trapped on its starting value and will never break. Iteration comes in two forms. Sometimes you are waiting for a specific condition to trigger, which is indefinite. Other times you know the exact number of steps required, which is definite. For definite tasks, like printing 1 through 5, a for loop handles the heavy lifting. Python automatically takes care of the initialization and update steps for you. Here is a simulated terminal. Try writing the ICU logic for a program asking for a password until the user types star. A for loop fails here because wrong guesses are unpredictable. The while loop perfectly handles this condition, changing based on user input. The rule is straightforward. Use a for loop when you know the sequence limit before you start. Use a while loop when you are waiting for a specific threshold or an unpredictable user event. Simply repeating actions is useful, but often you need to track your state over time without overwriting your past work. We manage this using the Accumulator Pattern. Establish an empty container before entering the loop. Initialize a variable, like total sum equals 0, to catch data each cycle. Placing this inside the loop body causes scope leakage, instantly resetting the container to 0 and destroying your accumulated data. To correctly track data, your variables must be initialized in the outer scope. That ensures they survive the repetitive execution of the inner loop body. Let's scale this up to a complex task, like tallying game scores with specific conditions. Even with nested logic inside the body, the loop remains stable. The outer initialization, control, and update commands hold the entire operation together. Keep this visual blueprint handy. On the left, the ICU framework guarantees your loop has the required mechanical structure. On the right, the definite and indefinite rules ensure you are choosing the exact right tool for your specific data. Loops operate on strict logic. Define your starting state, set a clear boundary, and guarantee your update. Stick to those mechanical steps, and you will write effective code every time.